to the stage Mr. Gary Birk with Tersus.
Oh, thank you. Okay, so my talk this afternoon is really on heat-enhanced, catalyzed, reductive bioremediation. And so what we're doing is we're adding an electron donor, specifically a vegetable oil, along with an alcohol. We're going to add a catalyst to that, and then additional heat. And the purpose of the heat is to increase the yield in this reaction that's going to create volatile fatty acids. And the heat will also help get the temperature to the zone where the dihalococoides or dihalobacter are in their optimal growth temperature range. And the term alcoholysis, so in the reaction we're adding an alcohol, and then the alcohol is going to become part of the reaction product, and thus that's the definition of alcoholysis. So today I'm going to give like an overview, briefly talk about optimal dechlorination conditions, and then average groundwater temperatures in North America. For there, I'm going to go into talk a little bit about catalyzed, enhanced, reductive bioremediation, how that chemistry works, and then from there move into why we want to add heat to the process to increase the yield and increase the efficiency of the dihalococoides or dihalorespiring bacteria, and then go into some heating options. So optimal, dechlorination conditions. Really, we need to have temperatures like between 15 and 35 degrees C, but the optimal is actually between 25 and 30 degrees C. And then the pH, we want to have somewhere between 6.5 and 8, and we need to really distribute the correct type of volatile fatty acids. So if we look at groundwater temperatures in the U.S., Sherry Scott, who manages our customer care for North America, recently got in a site evaluation form for a site in south of Miami. And the temperature there of that aquifer was 28 degrees C. So really that site's already at optimal, perfect conditions for reductive dechlorination to occur. But as we move up north, the temperatures aren't going to be nearly in optimal conditions. So we go to Canada, they're in the single digits, and across the U.S., the mean temperature for groundwater is roughly going to be about 15 degrees C. So now I'm going to speak about catalyzed, enhanced, reductive bioremediation. This is a process that we've been working on for a significant period of time with our colleagues at OU doing various research, and this is a process that we developed to address the distribution of volatile fatty acids. So I already gave the definition of alcoholysis, where we have a reaction in which the alcohol is the reactant and becomes part of the reaction product. So we're going to add some alcohols to the system. When we add heat, we want to make sure that the alcohols we choose don't have an azeotrope, so we choose alcohols that do not have one. And then transesterification, that's the chemical conversion process of the triglyceride. So soybean oils are triglyceride. You have 3 fatty acids on a glycerol backbone. We're going to break that backbone. We're going to have an alcohol in the process, and we're going to generate fatty acid esters with the aid of a catalyst. And so the way that chemistry works, we have vegetable oil. I'm showing here the triglyceride. We're going to add to that a catalyst, what we call EDS activator. So that's like an alkyl oxide with excess alcohol. So for every 1 mole of vegetable oil, we really need 3 moles of an alcohol in this process. And with that process, then we're going to generate some glycerol, hence alcoholysis, as well as some fatty acids and then carboxylic acid salts. And then so for our activator options, we really have, we've looked at 2 different types of activator options. One is like a hydroxide base catalyst for transesterifications. And then really you have the various types there. You can have sodium alkyl oxides or potassium alkyl oxides. We prefer the potassium-based alkyl oxides. If you're going to make soap, for example, your bar soap is made with sodium hydroxide. Liquid soap is made with potassium hydroxide. So we prefer to have potassium-based materials. Also, potassium, when you look at nutrients you want to, it's one of the nutrients that you potentially also want to add to the system. You can also use enzymes for the biocatalyst, but unfortunately, we haven't really spent a significant amount of time with that. And so if we look at why we would want to add temperature to it, you can see this is where we're using 1% of a catalyst, and I'm plotting, this plot here is temperature versus fatty acid yield. As you can see that the yield goes up as the temperature goes up. And then if we look at if we hold the temperature to 65 degrees C with a 1% by weight catalyst, you can see we're going to kind of plateau out within roughly, 30 to 50 minutes, and the yield is not going to significantly improve with additional time. So the reactions, do occur fairly quickly. If we look at the temperature effect, the yield of an enzyme, for example, that's going to have like an optimal temperature range of 55 degrees C, which would generally produce about 81%, 80% volatile fatty acids in a laboratory, for example. But generally above 60 degrees C, what happens there is that the proteins and enzymes begin to break down, and so it's going to lose its structure, and then the efficiency just isn't there anymore. So I'm going to now switch and talk about some example projects that we've completed. This is a TCE site in Australia. We're roughly about 2.8 or a little less than 3 milligrams per liter TCE. They used the prime wave to inject the material, which is also like a pressure pulsing system. They injected like 75,000 liters of the product. It took them about 2 to 3 weeks to do this application. Here's just some photographs showing the injection with the equipment. They were able to inject in multiple points at a time. And here I'm showing a photograph of the pressure pulse, the prime wave system that goes on a wellhead. This was a really tight clay aquifer, and hence that's why they used the pressure pulse system. But we really got pretty good results with. They estimated perhaps in 13 weeks we got 95% mass removal. So you can see going from almost 3 milligrams per liter to 33 parts per billion, and then right there in the source area, and then a little bit down gradient, like 1.3, 1.4 milligrams per liter to 56 parts per billion. So fairly good destruction of the contaminant in a short period of time. This is a site in California showing the injection scheme here. John Sankey, our representative out there, did this design. And so that they targeted this dosage based on the concentrations in the aquifer. And here are the results. And so what we're plotting here on the one on the left is TC concentrations pre and post injection, and this is 3 months out, and you can see we got pretty good destruction again, substantial reduction in contaminant mass. And then if we look at the D. helicocoides growth, we have also pretty good increase in the population of the microorganisms. So when we add heat to the process, the reason we would want to add heat is because it enhances the transesterification reactions. Generally, it's going to make it much faster, so we're not waiting for months for the reactions to occur. It's going to be happening within days to weeks. And then also that we're going to be within the optimal growth temperature for the D. helicocoides, and so that's really between 25 and 30 degrees C. We still have abiotic and biotic destruction at less than 45 degrees C, but above 50 degrees C, we have really very little abiotic or biotic destruction as well. So when we're looking at the temperatures, we need to be careful that we don't want to raise the temperature too high. And so if we look at hot water versus cold water, other advantages there, I'm from North Carolina, we drink a lot of sweet tea there, and the way they make sweet tea is, they boil water and they add sugar to it. And within hot water, you can put a whole lot more sugar than you can in cold water. And the same thing happens when we're adding, hot water. The advantage there is we're actually removing a lot of the oxygen. We did some studies at the University of Oklahoma where we actually we used a biodiesel product, and we degassed that product, removed all the oxygen from it and all the other gases, and we degassed the water, and when we added water to the degassed water to the degassed biodiesel product, for example, we were able to emulsify that material without any surfactant chemistry. And so the other key advantage there is, hot water dissolves more solids like sugars or soluble donors, so we can get more donor dissolved in this solution. So heating options, conventional, we've got in-situ thermal, and I would encourage you that, if you're doing a project and you're looking at doing electrical resistant heating or thermal conductive heating, that you go ahead and place some donor down gradient, because you're putting in a lot of energy into that system anyhow, and so that energy is there to already heat that aquifer, and you're going to take, it's just a great opportunity to take advantage of it. We at Tersus in 2020 and 2022, we did a significant number of projects where we went back to where they did electrical resistance heating at sites. The aquifer had cooled back down to ambient conditions, and they still had contamination, and so they injected donor at that time. If they would have injected donor at the beginning, down gradient when they had, or even after the aquifer starts to cool, they could have already taken advantage of that system and of all that money that they spent on putting that energy in to heat that aquifer. So that was just not well spent. And I kind of look at it like 20 years ago when we were doing these type of projects. We would always wait to bioaugment. We would inject donor and then come back, are the conditions right? Did the bugs grow up? And then we'd come back and bioaugment. Today, on every project we're doing, basically we go ahead and bioaugment right from the start. And so I think, I see that going on in the thermal remediation in situ, that, when they're adding ERH or thermal conductive heating, just to go ahead and add donor down gradient, take advantage of that money spent. Other options, and if you're going to do a project, that's a pretty significant cost. It's not worth that amount of money to spend just to do heat-enhanced bioremediation. There are lower cost options for there. You can look at using hot water boilers, shell and tube heat exchangers, or solar collectors, for example. We have a project that's getting ready to start in the Carolinas, and I would encourage you, when you're looking at your sites, to look at the infrastructure that's already there. So this is a manufacturing facility, and behind they have a boiler, a gas-fired boiler on the plant that is operating every day. And so right there in the plant area, really close to where that gas-fired boiler is, they have chlorinated contamination beneath the plant. And on the other side of that wall is where they're going to want to clean up this plume area. And so that infrastructure is already there, and it's being operated. So at this particular site, we're just going to tie into that boiler, use that hot water to add to the solutions and inject it. And it's, it's going to be a low cost because the client is already paying to operate that system anyhow. So I'm going to show some modeling results. This is for a project where we're getting ready to ship in the next couple of weeks, a tanker in one of these shell tankers that are insulated for transporting heated fluids. So this is in the Midwest. It's a sand lithology. The porosity is 0.33. The K is 1 × 10⁻². And then the hydraulic gradient is 0.002. So the groundwater here is moving pretty quick. And so what we did is we modeled a 12-hour injection event where we were injecting 75 meters cubed of water at 150 meters cubed per day. And we wanted to see how long it would take to inject this 90-degree C water, and then how long it would take to cool down to where we could bioaugment at the site. And so this is at half a day and 1 day. We're still now at ambient. The temperatures are in the 40+ degrees C. The aquifer temperature here was probably around 10 degrees C. 1.5 and 5 days. Really, but somewhere between 1.5 and 5 days, the temperature is going to be ideal at around 45 degrees C to bioaugment. We're in communication with the folks at Serum that manufacture the KB1 Plus and KB1 cultures. And while they believe that we can inject that culture, they have some data at higher temperatures. What we want to do, since this is kind of a pilot study site, proof of concept, we want to monitor the temperature and wait till it gets down to 45 degrees C before we go ahead with the injection. And then here I'm showing still we're at 10 days out. We're within the optimal growth range. 30 days out, 60 and 90 days out, we're still within the optimal growth range of the culture. So it's, we're going to really boost up the kinetics and grow a significant amount of bacteria by just injecting some hot water. And so if we look at what it's going to cost to do the pilot for the hot water injection, we found a contractor that's fairly close by that has one of these insulated semi-tanker trailers and has a boiler. I guess they do, industrial cleaning type operations. And so the cost for them to deliver 6,000 gallons, so we're going to test one area where we're going to inject hot fluids and another area where we're just going to inject, tap water, cold water, and see the difference after we bio-augment there. And then so it's less than $8,000, and of course they have a demurrage charge, but this cost is a whole lot less than bringing in all the equipment to heat it up on site. The infrastructure, whether it's propane tanks to fire it all up and all. And so if we're looking at options for heating, there's more mobile boiler units. I'm showing some smaller systems versus larger systems here. And if we look at the cost to operate, these, they can, for the smaller systems, you're looking at probably just $12K a month in renting. And then the hot water storage tank, $3.5K or so. But a turnkey type operation with a larger boiler unit, on a semi-flatbed with, bringing in all the infrastructure, it's going to get up there. It's some significant expenditures. And so, really there we're getting almost into the cost of, doing electrical resistance heating or thermal conductive heating. So we went back to the drawing board to see, hey, what can we do? What's available? So this is a project that one of our associates did in Mexico. So this is, these solar tube heaters. And you can see here, he got it up actually to 72 degrees C. There's a tank there in the background to store that heated water. But then, everyone thinks, oh, this is a great idea, but if you're going to look at the capital cost to install this, what are you going to do with it after the job ends? And so, it's still, while it looks like a fantastic idea, we're using the sun, it still has a cost, and then what are you going to do with it? Well, maybe that they, if it's an apartment complex and they need some hot water, it's a great idea, but, it's not for every project. So we've looked at, these, for example, laundromats, they have industrial-sized tankless heaters. And the key here is looking at the water heating capacity. And so, ideally, these units, they can run from 6.5 gallons per minute flow rate to 4 gallons per minute flow rate. So, you consider that on average well, we're only going to be injecting maybe a gallon a minute. So one of these units are pretty well sized for that. But the key is looking at it, and when you're designing these systems, is your delta and your temperature. You want to look at the temperature rise that you need, and so for a system that has a temperature rise, let's say between 36 and 55 C, if you have 15 degrees C water, that's going to give you an in-situ temperature of your water somewhere between 30 and 40 degrees C. So, and these systems are just a couple of $1,000. Plus, and then the other advantage there is they can run on, like your propane tank that you would use to connect your barbecue grill to. So they're pretty inexpensive to operate and are significantly less, of a lower cost type solution. So, in conclusion, microbes that do all the work, for the process, they like a warm environment. Ideally, somewhere between 25 and 35 degrees C is optimal for their growth. Alcoholysis is somewhere between 25 and 30 degrees C for respiration. So once we get this we get the water to that temperature, we inject the bacteria, they're going to build up, grow, multiply, and then we're going to have a significant population that can then respire the contaminants. Warm water, as I mentioned, has less dissolved gas. We can put more donor into warm water than we can cold water. I talked about our research where we looked at degassing, the waste stock from biodiesel, which are essentially just fatty acid esters, vegetable oils, and then mixing that just with water. And we degas both in the laboratory. We can form an emulsion without any surfactants. And then lastly, heat is going to significantly increase our transesterification reactions. When we've done it without heat, those reactions can typically take about a month. So with heat, we're going to reduce that time to hours to days. And so it's going to be significantly faster. The other thing is, if you're looking at a project, if you can compare it to EVO, essentially we're going to inject the same amount of mass of EVO. The only thing is we're going to use it up, we're going to create the volatile fatty acids that are going to be used by the bacteria to form hydrogen and acetate much faster, and so we're going to get reductive dechlorination occurring much faster. But then there's the question about what about back diffusion? You're going to have to, essentially though, that in a column in the laboratory, maybe we can get at the temperatures we're working at maybe 75% yield. But in the field, we're not going to have that. So we're still going to have excess EVO in the system to deal with any type of back diffusion. And then lastly, about droplet size, once an EVO is injected, and you want to inject it, it's going to have, because it has droplets, it can distribute pretty far. The same thing's happening. We're injecting the EVO solution, but then we're going to break it down much faster. So we're going to create that. It's going to start to ferment, go rancid, and we're going to increase that breaking down of the product into volatile fatty acids much further. So once an EVO is injected and starts to go rancid, you're losing your droplets there anyhow. And with that, I know we're taking questions at the end. So.
That's a lot of talk about alcohol.